Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in previous lecture we have seen counting of zeros. We have seen some theorem and corollary and some problems on counting of zeros. Okay, so today's we will see most important theorem, that is Morera's theorem. So there may be the question in your examination, state and prove Morera's theorem. So this theorem is very important exam point of view. So what is the statement of this theorem? Let us see the statement. Let G be a region and let f g to c be a continuous function such that integral over curve t f of z dz equal to 0 for every triangular path t in G. Then we have to prove that f of z is analytic in region G. Okay, so this is the statement of the Morera's theorem. Now we will see the proof of this theorem. Okay, so to prove that this theorem f of z is analytic in region G, we have to show that f of z is analytic in every open disk containing in region G. Okay, that means we have to prove that the f of z is analytic in open disk which is containing in region G. So for that, let us we suppose that a open circle or open disk whose a center A, radius R, which is contained in region G, and A is any point where A is any point in region G, R greater than 0, such that R greater than 0, then it is sufficient to show that f of z is analytic in this disk, that is with center A, radius R. Okay, so to prove this theorem, let us we take the any point z0 in region G. So let us we take the z0 be the any point in region G. So let us we consider this is the open disk whose center A, radius R. Okay, and let z0 be the any fixed point in this circle. Okay, and which is contained in region G. Okay, so therefore A z0 za will form a triangular path in a circle, open circle whose center A, radius R. Okay, so this is the center A, this is the radius R, and z0 be the any fixed point in region G, and take and z be the variable point in an open circle whose center A, radius R contained in the region G. That means this will form a path, that is A z0 z A, that is A z0 z A will form a triangular path in an open circle whose center A, radius A, center is A, radius R, or we can see the open disk. Okay, but given that integral over t f of z dz equal to 0, where t is a triangular path in region G. Okay, so what we have seen the triangular path, that is a z0 za. So therefore t equal to triangular path. So integral over t, that is triangular path a z0 za f of z dz equal to 0, we can write. Okay, now we will split this integral to a z0 z0 z za, a to z0, z0 to z, z to a. So first integral will be a to z0 f of z dz, plus second integral z0 to z f of z dz, plus third integral z to a f of z dz equal to 0. Let us consider equation number 1. Okay, now let us we define a function capital F in region G in a complex plane CFG to C as capital F of z equal to integral a to z f of z dz for all z which is belonging to open disk whose center A, radius R. Okay, so at a point z0, so f of z0 equal to this can be written as integral a to z0 f of z dz for z0 belongs to open disk at a point z0. Okay, so this is the for all z, and this is the at a point z0. Okay, so therefore using this in equation number 1, then equation number 1 will becomes a to z0 f of z dz plus z0 to z f of z dz minus a to z f of z dz equal to 0. Okay, so equation 1 can be written, we will interchange the limits z to a, that is a to z. So there this means this will be becomes minus a to z f of z dz. Okay, now putting the value of this integral, that is a z0 to f of z in this equation, so we will get, instead of this we will put this value, that is f of z0 plus integral z0 to z f of z dz as it is, and the value of dz, that this can be written as, that is f of z minus f of z dz equal to 0. Okay, so we can club this term f of z and this term, or we can transfer this term to RHS side, that is f of z minus f of z0, and left hand side is, that is integral z0 to z f of z dz. Okay, so we can write this step from this previous step. Okay, now we will divide z minus z0 on both side. Okay, then we will subtract the term f of z0 on both side. Okay, first we will divide. So dividing z minus z0, that is f of z minus f of z0 upon z minus z0, and then we will subtract f of z0. Okay, from this left side as well as from the right side. So first we will divide z minus z0. So 1 upon z minus z0, first integral z0 to z f of z dz. Okay, minus f of z0, subtracting this term to RHS side, f of z0. So this can be written as 1 upon z minus z0 integral z0 to z f of z dz. Okay, so this integral can be written as 1 upon z minus z0 z0 to z f of z0 dz. Okay, so we can write this integral in this form. Okay, so if you solve this integral, you will get this term, or we can say that this term can be written in the integral form. What is the next step? Now here z0 to z0 to z term is integration is same. So therefore we will club this term. Okay, and taking 1 upon z minus z0 is common term. So f of z minus f of z0 upon z minus z0 left hand side as it is. So taking 1 upon z minus z0 is common term. 1 upon z minus z0 integral z0 to z f of z minus f of z0. So taking in combine this term, and dz is common. Now we will take the modulus sign on both sides. So modulus of this term is, that is mod f of z minus f of z0 divided by z minus z0 equal to mod 1 upon z minus z0 integral z0 to z minus f of z minus f of z0 dz. Okay, so by using the property of modulus, this can be written as left hand side as it is less than equal to, take the modulus of each term. So less than equal to 1 upon mod z minus z0 integral or z0 to z mod f of z minus f of z0, okay, into mod dz. Let us we consider equation number 2. Okay, but now we have given f is a continuous function on region G. Okay, so if f is a continuous function on region G, then we can say that f is also continuous on a open disk whose center a radius r. Okay, so therefore f is a continuous at a point z0 and z0, which is a point which is lies inside the circle and which is contained in region G. Okay, so therefore we can say that f is a continuous at a point z0 belongs to open circle whose center area radius r and which is contained in region G. So therefore by using the definition of continuous function, for every epsilon greater than 0, there exists delta greater than 0 such that mod z minus z0 less than delta, which implies mod f of z minus f of z0 less than epsilon. Absolute value of f of z minus f of z0 less than epsilon. Okay. So using these values in equation number 2, then equation number 2 will becomes, we will put the f of z minus f of z0 in equation number 1. This value in equation number, in equation number 2. Then equation number 2 will becomes mod f of z minus f of z0 divided by z minus z0, uh, here is a mistake of term, so this should be the f of z0, f of z0 term. Okay, so this term will be here, this term will be here. Okay, so here we have written correct step. Okay, here is some mistake. Okay, so you have to add minus f of z0. Okay, less than 1 upon mod z minus z0 integral of z0 to z, and value of this term is from this equation, that is epsilon mod dz. Okay, so less than 1 upon z minus z0, epsilon is a constant term. The integration of this term will be the z, upper limit minus lower limit, so you will get z minus z0. So z minus z0 and z minus z0 will get cancelled, only there will be the remaining term, that is epsilon. Okay, so therefore by using the definition of the limit z tends to z0, f of z minus f of z0 upon z minus z0 equal to f of z0. By using the previous reverse definition of the limit, we can write this step in this way. Okay, so this is nothing but that is f dash of z0 equal to f of z0. So hence we can say that f is a differentiable function, and hence it is a continuous at a point z0. Okay, so if we repeat the whole process starting from the f dash of z, then we get f double dash of z0 equal to f dash of z0. Okay, so continue in this manner. If you differentiate again, or if you repeat again these steps, so you will get f triple dash of z0 equal to f double dash of z0. Okay, so in this way we will get f fourth of z0, f5 of z0, and so on. Okay, so thus in general we can say that f dash, f double dash, f triple dash, f fourth dash, and so on, whole derivative will be exist at a point z0. Okay, and we know that z0 is a fixed point in a open circle of center a radius r. Okay, but z0 is a analytic, but z0 is a any arbitrary point, not analytic. Z0 is any arbitrary point in a open disk whose center a radius r, which is contained in region G. Okay, so therefore f is a differentiable at every point on a open circle whose center a radius r. So this can be read as open circle or open disk. Okay, so if the function is differentiable, then we can say that that function is an analytic function. So which implies f is an analytic function on a open disk whose center a radius r. Okay, so if this is the analytic on open disk, then we can say that which is analytic on the region G. So f is the analytic in the region G. So that is f of z is analytic in the region G. Okay, so here the proof of this theorem is completed. Hence, this is the complete proof of this Morera's theorem. Okay, so dear student, this theorem is a very important exam point of view. There may be the question in your examination. Okay, so you have to carefully read this theorem with statement. Okay, state statement and also proof of this theorem. Okay, so this theorem is a very important exam point of view. You have to read carefully. Okay, so step by step you can see how is it proved. Okay, so we will stop here. In next lecture we will see the another theorem.